Okay, just to keep to the timing, we're just going to start, and then I suppose people will just come in as in when they can. Today is lab session, right? So we'll just go through the assignment 2, the first few parts, to get you guys started on being able to implement the backpropagation models and solve the problems that are put in the assignment. But first, to remind everyone that the hot field network assignment 1, should be due tonight. So if you haven't done so already, please upload it to the NTU Cool system. Okay, and if you do have problems and if you need more time, as always, just let me know. I'm pretty flexible on that. For now, we have time, so we are not too pressed on time. Okay, so let's go to the assignment 2 proper, and let's just go through it and to orientate you. So this is going to be similar to the hot field assignment 1 type of format, in that the first part is to actually help you to implement your model, which essentially is what I have gone through with you last week, right? In the Colab code that I have and shared with everyone. And as always, please feel free to use the code because anyway, I only give you the initial parts. But if you can, try at your own hand at making your own code if you want. There will be different levels of benefit. We do this, I give you this code is because some people might be not as familiar with coding, and I didn't want that to be so-called too big of a penalty. You still need to know some coding, of course, to use the code that I give you. But if you can and you can do it yourself, then you will get even more benefit. Okay, so let's go through the first assignment 2, first part. And that's part 1 is to get you to try out some exercises that instantiate category learning. Okay, so remember again the multi-layer perceptron using backprop learning. The idea here is that this kind of setup can allow the network to map anything to anything, right? As opposed to the hot field network, which is mapping itself, auto-encoding. So that's a bit more constrained. This is a bit less constrained. And one of the things that you want to map, when you want to say you want to map anything to anything, one psychological phenomena that you can do is, for example, you can learn categories, right? You can see a bunch of different kinds of stimuli, and then you can say, oh, all these different pictures, they're all cats. Or all these different pictures, they're all dogs, right? And so that you learn a dog and a cat category based on different features that define the objects or items that you are looking at. So this is category learning. And so we want to test and see how a MLP doing backprop can learn categories. So to do that, we implement a 1-layer network. 1 layer means you have 1 layer of connection with 2 layers of nodes. So it's the input node layer with 1 layer of weights, and then the output node layer. Okay, and backpropagation. It's a backpropagation network and a 2-layer backpropagation network. So you have a 1 layer and a 2 layer. So we'll try out both. Okay. Explore the parameter space yourself, but you might start with eta, which is the learning rate at 0.3, and the momentum, which is the memory rate, so to speak, at 0.7, and change them to get better fits if you want. All right? Train both networks on the 3 sets of training patterns described below, or on training patterns of your own design. If you design your own patterns, make sure they have the same critical properties as the sets below, and describe your network's architecture, activation function, training, learning rule, right? And stop after 1,000 iterations if your networks do not settle. So this last one is sort of related to the question last week about what if we have a loop where it doesn't learn anything and it keeps going, or it is learning but it doesn't seem to be learning fast enough. Hey, the hard set to avoid your computer burning up here is basically try 1,000. As a reasonable rate, okay? And it is recommended that you use one output unit for each category. We'll talk more about this later when you see the data table. You can deviate from this if you wish, but we can try this out we'll try this out later as the basic application. And you can decide for yourself how many hidden units to use in a 2-layer network. So if it's 2 layers, if you can visualize, it will be the input, then 1 layer of weights, the hidden layer, another layer of weights, and then the final output. So that makes it 2 layers. So you have hidden units, and you can decide how many units you want in there, and you can evaluate your network accordingly. So test the ability of both networks to classify deviations, which is those distortions, those probabilistic distortions of the trained patterns. So basically you train them from the original data, but then you test them on noisy patterns, and decide and describe how you create these noisy patterns. Okay, so all this is to kind of get you to frame your thoughts and your simulations in a very organized way. So your ultimate goal, okay, is to compare and contrast the properties of these networks and answer what patterns can these networks learn, why, how fast they can learn. So you need to have indices of their learning progress as well. Okay, so for example, how many exposures do they need to reach some level of criteria? Meaning how many times do you need to tell them this is a dog, this is a dog, this is a dog, right? Before it actually learns that this is a dog and that is a cat, something like that. And what are the generalization capacities? So like, what if I give you something that was not part of your training set? Can you then recognize that this is a dog or a cat? That's generalization. Okay, so and all that. So this is the data table for set 1, non-overlapping categories. So here we define, again, we go back to a binary data table in the original. But if you remember last week, the output of the network I give you will not be binary, right? Because the sigmoid function is continuous. But it will approach extremes close to 1 and close to 0, all right? Or it should, all right? And so then you can take that as almost binary, okay? So non-overlapping categories. So for the first set, you can see that there's category A is either this 10-bit word or this 10-bit word. Category B is either this one or this one. C is this one or this one. And D is this one or this one. Okay? So there are 4 categories, but the inputs are 10-bit words. So this, by definition, means that your input layer, the nodes, has to be a 10-bit, 10 units. And your output has to be 4 unit output, right? We said here, yeah. Excuse me. Cool. Okay, you can use 1 output unit for each category. So if there are 4 categories, it is recommended that you will have a 4-bit word as the output, which is 1 unit per category, so 4 categories, right? You can do that. However, you may deviate from that if you want, which is, for example, you could do a 2-bit word to still represent 4 categories, right? Because it can be 0, 0, 0, 1, 1, 0, or 1, 1 is still 4 different states. So a 2-bit word can definitely code for 4 different categories as well. For now, just to keep it straightforward, you use a 4-bit word to code for 4 different categories. Of course, if it would seem 2 bits should be the minimum for 4 categories. Okay, you can use 3 bits if you want. 4 bits, anything more than 2 bits is a redundancy. Okay, but there might be different efficiencies depending on the structure and the nature of the data. Okay, but we will start with a 4-bit word as the output. So 4 bits meaning 1 bit per category. And these categories that are learning, as you can see, they are non-overlapping. None of the active states are found in any other categories except itself, except its own category. Okay? So let's try this one. And you'll see that this is what I've encoded in the last week's pattern. And then we have this input, and this is what we mean by a 4-bit word, right? And each bit encoding one category. You can see that the active state is for each position on the 4-bit word. And there are 8 lines, I believe. Yeah. No, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, 8 lines corresponding to the 8 input training patterns that we want the network to categorize. Okay? So this is the input, this is the desired output, this is the data table, the problem. And we did last week already, we had the training network, just refresh your memory. And so please get your computer set up so that we can try this out, and then we'll have people present your problems or your solutions. So we have the training network, TrainNet perceptron, and the testnet perceptron codes up there, and the distortion pattern ones. You can take some of this from the Hopfield instantiation. Okay, the rest are just visualizations. But so the key is we have this input output, and we have these hyperparameters. We said that the maximum epoch to train for, if it doesn't settle, is 1,000. And we set the error requirements above which the network keeps training. Means for each epoch, you want to try to make the error reach 0.001, then go to the next epoch. Otherwise, it will keep trying to do gradient descent until it has reduced the error to 0.001. Okay? And the learning rate and the momentum are as such here. And so this trains the network. And for now, I have done a network where I have done the 2-layer network here. But why don't you guys try the 1-layer network on your own, okay? And then see what your outputs are. You can, of course, go ahead and try the 2-layer output on your own. So, and this is fun because, I'm doing 10 input, 20 hidden, and 4 output, okay? Why don't you guys try 10 input and 4 output and see how it does, okay? And then you can try the visualization and you see how its performance. And to do that, to evaluate it, you can test the train weights, okay, on, let's say, one of the outputs, and you define the architecture, and then you can see whether the output is as you might expect. So like this is pattern 3, which is category B. So you can see, yeah, this is showing you category B kind of response. This is very high, and the rest are close to 0, okay? All right, so I'm gonna let you guys try it out, and then let's say about 10 minutes, okay? And then after that, we go one round, and then let's show everyone what's your solution. Again, you want to try it out, my recommendation is you can try a 10 and then a 4 without the hidden, okay? And then you see how the network performs, and then show us how you evaluate it and all that kind of stuff. So let's take 10 minutes. Now it's 9:30. I'll check in again at 9:40, and then we'll go one round. You have those HDMI cables on your table and the microphone, so that later we go one round, you can share it. It's pretty easy. Okay. We're trying out the assignments. Yep. Okay. Shall we go one round? It doesn't matter if you've completed. Maybe just update everyone about where you're at. Let's go one round and then let's see, maybe, yeah, why don't you start over that side and then we go counterclockwise. Is that okay? Yeah, we just have to share where we are at. It doesn't have to be that you've solved the problem. So let me see how we set. That one is 前右，对不对？ I always cannot. Is this it? This way? No, yeah, you go ahead and set up your screen. I 应该是 you have to change the input. 好像是这个。要先对。I forgot how to do it. Yeah. HDMI. Okay, now 等一下哦 Wait. Oh, okay. So 是这样。She's upside down. Okay. All right.
So the above are some function settings.
Yeah. Okay.
And when their networks, just your set one. And output. And parameters.
Okay.
So this is a training process.
Yeah. So this is 10 and 4. Okay.
Yeah. And distort the first line of your
set
input.
0, pattern 0.
This.
Okay. So we expect if it's learned, then it should give you 1 0 0 0, right?
Yeah.
Yeah. And does it? Looks like it does.
Sorry.
Looks like it does, right?
Yeah.
1 0 0.
Sorry. I changed one.
What's AP?
The distorted.
Oh, right. Okay. So set 1 is the original pattern.
Yeah.
Okay. Got it. Oops.
Sorry.
Still weird, huh?
Wait.
Oh, I see. Okay. Because AP is just one vector.
Yeah.
It's not an array.
Yeah.
Okay. So, and so should AP be giving you, because this looks like pattern 2 or pattern B? Is that right?
What?
The output is 0 1 0 0. This one. Is that expected, or depends on the AP0? What was trained for AP0?
What was trained for AP0?
Yeah. Can you go up to see where your distortion is being done? So you were distorting set 0, set 1 0 at 20%. Why don't you try 10% and see? it will
10%.
give you, because we expect set 0 to be 1, 0, 0, 0, right? Yeah, yeah, let's take a look. And then what is set? What is that set? So set 0, can we take a look at set 0 again?
Set 0 is this.
Is it? Okay, all right. Yeah, yeah. Okay, so AP0 is essentially, it didn't do any distortion.
Yeah.
Okay, so let's test it first to make sure it behaves properly. AP0, let's try it out. Okay, so it's okay with that. Yeah, so then let's try 20% again. And let's see. Okay, so it's a bit weird, so then let's try it out. Okay. Oh, wait, but you see, it's not, it's breaking, right?
Oh.
Right? Yeah. So this might happen, but you have to see, maybe it is because the training is not done effective, or maybe it's because of this, right? It's not that it must be perfect. I mean, because note, this is no hidden layer, right? So this is effectively still a single layer perceptron. Okay, so note these. So in other words, you're trying this. This looks, it's doing what it's supposed to do in terms of code-wise, yeah. But maybe, so now you want to maybe try it over a few loops to evaluate the different situations, right? So note this. Find a way to log this over a few times somewhere in your code. Or have you done that already? Not yet, right? Okay. So why don't you try that? So every time, maybe you have 8 different patterns, right? And using the 10-4 kind of structure, see what are the different outputs you get for each of the 8 different inputs. Does that make sense?
I still think more familiar with it.
More layer will work.
I mean, I'm not so familiar with the meaning of the output.
Oh,
actually.
You mean this one?
Yeah.
Okay, so you train the network on the original set 1, pattern 0 to pattern 8, right? Sorry, pattern 0 to pattern 7, right? So the input, if you go up to the data table, yeah. So you trained the MLP on, this is category 1, or a category A, B, C, and D, right?
Yeah.
These are the 4 categories. And what does it mean by category is, this is category A, B, C, and D, correct? Okay. So what we want the network to do is that if I give you 0, 0, 0, 1, 0, 0, 0, the network should output 1, 0, 0, 0. And if I give you 0, 0, 0, 1, 0, 0, 0, 0, this one, then the network should output 0, 1, 0, 0. Similarly, if I give you 1, 0, 0, 0, 1, 0, 0, you should output 0, 0, 0, 1. Okay, so that is the ideal. This means that if I give the network these 8 different patterns, each of these 8 different patterns should be mapped to the corresponding 8 different patterns here, which are equivalent to 4 different categories of different kinds of outputs. That's clear, right? Okay. So then when we distort, when we put the distortion, it's the same thing as we did before. Originally it's 0, 0, 0, 0, 1, 0, 0, 0, but if you distort by 20%, sometimes the 1 or the 0 gets flipped, right? So it's like originally you give it a cat, and then the cat is a red cat, right? You train it on red cats and blue cats. But now you distort it so that it becomes a green cat. But it still has all the other cat features. So does the network still recognize that even though it's just changed one thing, color is changed, but the rest of it is still a cat? So it still recognizes it as a cat. Okay? So now you give it, so you distorted it and you gave it a green cat. All right, so the network has been trained on recognizing red and blue cats. Okay, now you give it a green cat, and you see that it gives you some output that it was not trained before. So right, this is none of the four outputs, none of the four categories, right? This is like 1, close to 1, 0, 0, right? Correct?
Yeah.
Okay, and as I said, because of the sigmoid function, the output will not be exactly 1 or 0. The sigmoid function is continuous. So what you expect is like numbers that are close to 1 or close to 0, right? And you can see that's what's happening here, except that the network is performing in a way that is saying something like 1, 1, 0, 0, rather than 1, 0, 0, 0, which is what we expect. So there's something off with the way this network is trying to categorize this kind of green cat distorted input kind of thing.
Oh,
Does that make sense?
I get it.
You get it? Okay, all right. So if you want actually, and you guys can think about it, if you don't like this kind of thing, what can you do? You just change the output to be, if it's greater than 0.5, then it's 1. If it's less than 0.5, then it's 0. In other words, you impose a binary ReLU function on this A output here. That will also, make it closer. But you don't need it, right? Because we humans, we can visually see that what this is. Yeah. Okay?
Okay.
All right. So why don't you try maybe some other input, and you see whether it still doesn't perform so well. And then the next round, you can try putting in the hidden layer. So like 1084 or 1024 and see how it goes. We expect that it should then be able to handle it better. Okay?
Okay.
Okay, should we go next person? If you're not ready, it's okay. No, I think you just connect it， 那它会自动就会抓到，你不用按那个，你要按 HDMI 啦，下面 HDMI 对。然后就按那个对，它只是比较迟钝一点，对 ，OK，all right。
Okay. So I think I did
Okay.
everything for so the input and the output and
Yep.
also the required parameters and
Yes.
the train weight for 1 layer and 2 layer.
Oh, you did
no,
both already. Okay. I
Yeah,
see.
the no hidden layer and with hidden layers.
Okay, so you encoded the weights as 2 different arrays, right?
2 different.
Two different arrays. So this is one array, and this is a different array.
Oh yeah.
And you just went ahead and trained both in the code. Okay,
Yeah.
got it.
So and also I just I plot the arrow, so it will be something like this.
Good.
Oh, and I also test the category. So
Okay, with distortion, or do you have distortion yet?
Oh no, not yet.
So this is just with the original input. You
Yeah.
want to test
Yeah,
whether
test the original
Okay,
input to
cool.
see whether it
makes sense. Yeah. And we expect that it should be able to do it if it's been trained on it. Right?
Yeah.
Yeah. Okay. So.
But the value sometimes is a little bit off. So
Yeah,
for
yeah.
example,
So wait, let me see what this is. So this is the input. This
And
is
this
the
the-
expected output.
yeah.
And this is for the no. So this is just a single layer, and this is with the hidden layer.
Yeah.
Okay. So you can see.
With one hidden layer is better.
Better. Yeah. Right. Yeah. Which is what we expect.
Yeah.
And then with the no hidden layer, which is effectively a single layer perceptron, looks like it can do it, but it seems like it's almost breaking also. Not so nice. But this is okay, right?
Mm-hmm.
Yeah. So your single layer is different from her single layer. So your single layer by chance, because remember the initiation is a random unit, random W for and so one thing is you can try again. You re-randomize and see if luckily you still get a well-behaved one, right? So this is something that is worth doing statistics. Like if I try again, every time I reset my random seed, my random setting, whether by chance I get a network that can, single layer that can still do it or not, okay? But then if we don't like chance, let's say we add one hidden layer. So regardless of where you randomly start out, as long as you have a hidden layer, you stably will always be able to solve, or more likely to solve the solution, the problem. Yeah, okay, so this is good. So what's the error like?
Actually, it looks pretty much the same.
Yeah.
So the orange one is with the hidden layer.
Yes. Yeah, so you expect, again, it's not bad, right?
Yeah.
Yeah, but you do expect that the one that doesn't have the hidden layer to have a bit poorer, require more learning to achieve that.
Yeah.
Yeah. Okay.
And I also try the different eta value.
Yeah.
So.
Different learning rates.
Yeah, different learning rates.
With
And
fixed momentum.
but I'm still.
Oh, you also changed them. Okay.
Yeah, I also changed the momentum, so it would be always add out to 1.
Oh, this is great. So just everyone take a look at this, because so what he's doing here is that this is what we call data mining for the hyperparameters. Okay, so hyperparameters are not trained, right? We decide that the eta should be 0.3, 0.7, or 0.5, 0.5, or whatever, right? Then the question is, why should we do 0.3, 0.7? Why not try 0.5, 0.5, or whatever? And the answer is, at least in this problem set, we don't know. We don't have a good reason why we want to do those hyperparameters. And if you don't have a good reason and you want to explore the hyperparameter space, so this is something we do. We set up an array of different hyperparameter combination, and then we try it out. Yeah. So this is very computationally intensive.
Yeah.
Yeah. Of course, this is a very simple problem. It doesn't feel computationally intensive. But let's say you are talking about an LLM with billions of parameters, then you will see it's very computationally intensive. Yeah, okay, so what did you find?
So, but I'm still haven't changed the input yet, but
Okay.
testing the input yet, but I changed the input, I changed the weight. So this the arrow looks like.
Okay, wow, so what's the blue one?
The blue one is the first one, like the eta value, the minimum, the lowest one, yeah.
Okay, so where mu is the high is close to 1 and eta is close to 0, which means that the model is very sluggish.
It changed very small.
Correct. Every time it learns, it remembers more than it learns new things. So you can see correspondingly, it does learn, but very slowly. It requires so much more, right? And the fastest one is this one? Green one?
Not sure. Green one?
That one.
Green one is actually, which one?
No, I saw this one is, this one is.
I think it's the last one.
Oh, really? I can't see.
I think I'm
the color, my color is.
I guess it's this one. It's because the green only has.
Is there a way to change the color scheme? Or you don't use different random color. You use from like lightest to darkest.
Oh.
Then that way we can easily see like this is the lightest is the poorest and then the darkest is the. Because like that is random, we can't really identify.
Yeah, I think there is the last one.
Okay,
yeah.
If you think so, then but go and validate it and check. Yeah, it might be, it's reasonable. And then this is plot lib, right? Is this matplotlib plot?
Sorry?
Is this plot, I forgot which visualization. This looks like a matplotlib plot.
It is, I'm using your function.
Yeah,
I changed a little bit, by the way.
Do you, I forgot whether I use plotly or I use matplotlib.
This one.
I think that's matplotlib. So yeah, so in other words, why? It's because then the plot is not interactive. So if you move your cursor on the thing, on the item, it doesn't tell you what that thing is. But if you use plotly to do that, plotly has a lot more info. So when you move your cursor, it will tell you, oh, this is that value.
Okay.
Yeah. So the only way for you to effectively visualize those error curves would be if you use a gradient color scheme rather than random color. I don't know. You can try and see if that will help.
Okay.
You know what I mean?
I know what you mean.
Yeah. Okay.
Okay, so that's what
So
I
that's
have
cool.
so far.
Okay. Very good. Thank you. So then try, there's other things to try. So you are only trying the single layer thing with this 20 hidden units, and then you're exploring the parameter space. But try with distorted input, and maybe try, maybe other hidden layer setups if you want.
Okay.
Yeah. Okay. Next.
你要
你要吗？不要，不行。你有 Do you want to try out and like see where you're at? Okay, that's fine. Yep. You want on this side? Who wants to go next? Should we go bend behind, like go counterclockwise? Does that work? Or you want to go first? 那边有啊。你要这个啊？这个。I see. Yeah. And then 这个是这边，然后那边要换，等一下帮你，可以。And then 要用这个 ，it was 你可以点 HDMI 吗 ？And then 那个 ，yeah，OK， 这样就可以，可以了。All right. You want to use the mic? Yeah.
I check out the linear pattern
Yes.
and use the character A, B, C, D. So output have to be the 4. So I try the one layer first.
Yeah.
10 input and 4 output, and try to see their error. They will directly almost close the 1.
Yeah.
Yes. And I try to also see the input, the number and output, and they can find the same pattern.
Is this distorted yet or not yet?
Not yet.
Okay, so this one A3 is the original training pattern. Okay.
Yeah.
All right. Okay.
So it's like the fully connect the 1 layer output.
Yes.
And I try the 2 layer and use the 10 input and 8 the hidden layer and the 4 output.
Okay.
Can see the little different curve than the 1 outer layer.
So what he did before was to put the 2 lines together. It might be easier to see the difference, right? Yeah, I mean, that's if you have time, you can work on that visualization.
Yes.
Okay.
So the hidden layer have the more time to close to the 1.
Okay.
And also see the pattern, the output pattern is different than the 1 layer to show out.
So let's pause here. So with 1 layer, it's only the input and the output you get, right? But with the hidden layer, you get the input, the hidden layer activity, and the output.
Yes.
Yeah. So if you have more hidden layer, let's say you do like 10, 8, 8, 4, then you expect like 4 arrays, right?
Yeah.
Okay.
So the different layer, they can show out the different results in here.
Yeah. Okay, very nice. So things to try would be to do the distortion and see how it goes, and then see if you want to do better visualize. Try to, because later on we are going to try more complex models. Then the visualization becomes more useful because you will more easily see how it works, how differently. Yeah. Okay, very good. Thanks. Let's switch over.
Hello?
Okay.
So to start with,
Yeah.
I set up pattern A just as, oh sorry, not this,
Yep.
just as assignment, and visualize it.
Yeah.
The path is as above,
Yeah.
and so I tried with
Your
hidden
direct-
layer first.
Okay, sure.
So it's the T2, and the output seems good enough. I tried with the
Okay.
fifth one.
So not yet distorted.
Yes, also not yet distorted.
All right.
It should be 0, 0, 1, 0. Yeah,
0010. Okay. Yes.
0.9, so it's basically 1, close
Okay.
enough. And then I try with no hidden layers.
Okay.
But I was wondering why
Oh, okay.
no hidden layers perform better compared to with hidden layers. No one knows why, so
No. So this is a good intuition. And that's the reason why we get you to try it. We have an intuition that the hidden layer should perform better than the one without
Yeah.
hidden layer, right?
should.
However, note that always we start out with randomization of the network, right?
Mm-hmm.
So you might have a chance where your single layer perceptron actually still performs pretty well, maybe even better than the hidden. We don't know, right? But this is like by chance, right? So the way to really validate is not just you do it once and you see like, it performed better.
Oh.
But you might have to have a loop. Remember the hot field? Same thing in the assignment, right? It's not just you do one time, but you do 3 times per thing and you try it. So altogether you
And
actually
average
run
it, yeah.
72 times or whatever, a lot of times. So similarly here, it's not just a one-time performance thing. You might think about, wait, does this happen robustly, statistically significant? So maybe you try a few loops to see like, hey, does it always perform better? Or maybe it's just by chance.
Oh, okay.
Yeah, okay? So yeah, so this is interesting. And you have this setup where you can compare 2 lines, so that's good. So think about how you want to try it out to validate this very curious thing. How come my single layer is performing sort of better?
With hidden layers.
Is it really performing better? Because what you can see is, what it's doing is, so no hidden layer is going down. But then at this point, it sort of flattens out earlier, right?
Yes.
But then the hidden layer is slower at first, but then it goes sort of almost deeper down, sort of. Very subtle.
in later, yeah.
Yeah. So, this kind of thing, when you see this, when you visualize your data, you see something, think about how you might understand this better. So for example, if it were me and I see this, I want to zoom in here to see what's going on here more detail. Because I can't tell whether it is a crossover or is it just meeting and then just joining together. You know what I mean?
Yeah, seems there's a crossover.
It looks like there might be a crossover, but it's not very certain. And it might be something like if you can visualize it, even zoom in or something, then maybe we learn something new.
Okay.
Okay? Yeah, so this is how you interact with your code. Like, I have my code that generates this fixed plot. But after seeing this fixed plot, I'm curious about even more detail. And I know the data must be there. So maybe I need to have another plot to zoom into this section or something like that.
Mm-hmm.
Yeah. So think about that.
We can do it.
Yeah, think about that. Okay?
And
All right. What's next?
so the AO3, the
AO3 is...
without hidden layers
okay.
seems good enough,
Okay.
but a little bit further compared
Right,
to
sure.
with hidden layers.
So if we binarize things, it will work. But
Yes.
if we maintain the original output and you do sum of errors,
I
it
can
will,
do sum
yeah,
of
you
errors.
right. So, and again, another, and for everyone to think about, if you just take a very loose criteria, binary-wise, this is fine. But if we encode it as just total sum of error, the single layer might still have more error than the hidden layer. Maybe.
Yeah.
Yeah.
So,
Okay, so those are things to think about.
that's all for now.
Okay, pretty good. Okay, next we're gonna go. Ben, you have any? Yep. Okay.
Yeah, setting it up. Make sure I set it up properly.
Yeah.
I'm not sure if that. Yeah, but this is. I copied over the array and then asked to see if they could like.
Hey, wait, your array looks a bit different.
Oh,
Is
is
it
it
the-
the first one? Is it? this
Set 1. This set 2.
Oh, set one.
Yeah. Set 1 is the non-overlapping. Set 2 is you see that they are overlapping. So that I
Okay.
noticed that. Yeah. Okay, so this is not the set 1.
No. Okay.
So you're going to get a different result, but it's fine. Let's take a look at what you have. So what you have is not non-overlapping. They are overlapping, but it's set 2, so they are linearly independent still. So though the active units might be active again in subsequent patterns, but the patterns are still independent. Okay? So non-overlapping, obviously, they are independent. But in this case, they are overlapping, but they're still independent. Okay? All right, so with that in mind, let's see what you get. Yeah. Okay, so you're trying the 10, so this 10.4, you have to change this. This is not the 10.24.
Oh yeah.
Yeah.
Okay. Yeah, that's where I'm at so far.
It's okay. Also, just the visualization?
Yeah.
Oh, okay. So how's it working out? Does it make sense to you, or?
Slowly, yeah. So
Okay.
it's pretty much.
Okay, so just sort that out in terms of this one, the visualization. Bear that in mind, because otherwise you'll trip up. This is, as we can, the visualization is showing more the 10.4 than the 10.24. Okay, and then check on your input. Make sure the input is the set 1, not set 2. Or at least if you're trying set 1. If you want to try. Okay, thank you. Let's go back to the assignment. And then let's move on. Let's see where am I. Okay. All right. I mean, I think everyone can pretty much get the first part is pretty easy. So, some people have been trying that out in terms of expanding it already. So not an issue. So for those of you who have only done 10.4. Try 10.24, okay? For those of you who have already done 10.24, you want to try the distortion, or you might even want to try 10.84 or 10.10.4, try to have all these various things and work on your visualizations, all right? And then we see if you can go push it beyond. Just are some other things in terms of in the script that I gave you that might help. I also have the visualize activation function, which is one of the visualizations I have defined above. I think it was it this one? Visualize. Yeah, visualize activation, this definition. All of this will give you this output here. And I'll just take this opportunity to walk through this output with people first before we go to the assignment, next assignment. So first things first is this very horrible looking color scale. What it is it will, I think I ran it already. Yeah, I did. So I might as well run it again, see if it works. Okay, good. All right, well, so this just means that it's not active, and this means it's active at the level of 1, okay? And then the visualization is, this is the input. So this is 0, 0, 1, 0, 0, 0, 0, 0, 1, right? Okay? And you can see with, this is plotly's plot. So you can see that when my cursor goes, the plotly actually gives you output. So this is, look at the z value, x, y, z, right? You can see x, y, z. Look at the z. The z here is 0, 0, and then 1. And 0, 0, 0, 0, 1, 0, 0. So this is the plotly function, and it's a little bit more interactive than the matplotlib function. So just something to share with everyone. So this is the input layer. This is the hidden layer with 20 units. So 20, x is 19 to x is 0. Okay? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 19. So 20 hidden units and 4 output units. Okay? So I'm visualizing my network activity state architecture using this look. And then I have layer 1 to layer 2 weights, and then layer 2 to layer 3 weights as well. Okay? So I can, in one shot, visualize the values, the numbers that are going into my network. If you ask me, is this interesting, or what does this tell me about things? Not on its own like this, but if, let's say, you want to evaluate the model in greater detail. For example, here's a bit theory, okay? Here's a bit of theory. So, if you recall, the way the backpropagation works is that we will forward propagate activity and then get some output state and compare it with the desired output, then we calculate delta, right? Then we get the delta, and then we use the delta modulate by the derivative function to change the input weights. So weight layer 1, we change these weights, right? Okay? Which weights do we change, more or less? Do we change all the weights, or do we change some of the weights, and by how much? By how much we know. By how much is determined by the change weight alpha plus momentum, that learning rule, right? But which weights do we change? So recognize that that's why the updating function in terms of the delta is also multiplied by the activity and the weights, right? So it's a selection, it's a filter. So in other words, it only changes the weights that most had greatest influence on the output that resulted in the error. And so on and so forth. It only changes the hidden weights, weight 0, that resulted in the biggest error in the hidden layer as well. So at this stage, you can't see it, but if you want to go deeper into the model, like each iteration, every time you learn and update, you can see that what it will do is it's not changing at every epoch. It's not changing all the weights all the time. It's changing only, let's say, this weight, because it's 20 to 4. So it might only change this weight and this weight, but not the other weights, right? And you can see how it's selecting, because that means that those weights have biggest influence on the resulting error, okay? And so on and so forth, like similar for weight 0. It might change this weight, those weights, but not those other weights. So you can see, so here is 0 to 1, right? So the red ones are where the weights are not changed or like dampened, and then the blue color ones are the ones, the deep blue color ones are where the weights are changed the most or contribute the most. Then why is this important? This is kind of like, if you go back to the brain, kind of like if I give you cat features, where are the weights, most contributing to the final output of the network is saying, oh, it's a cat. So it almost be like or saying that it's a dog, right? So it's almost like you are scanning, if you do fMRI, you are scanning your brain, and then you see a bunch of activity in, let's say, fusiform inferior temporal gyrus when you show them these features, the brain these features, and then the person says it's cat or dog, right? As opposed to some of the other regions, so the red color regions, which are not involved in this computation at all. Maybe like the, I don't know, parahippocampal gyrus, about scenes, processing big areas. So it might be, this might be one way to equate it to the brain, to say like, oh, the red color regions are maybe like the parahippocampal area in the human brain, and the blue color regions are the fusiform gyrus when doing this kind of task. Okay, so this visualization then becomes useful, right? Okay, so for now, we're not there. This is a bit more advanced, but we're not there. But just to introduce this to you, if you have time and you want to code it into your coding schedule. Okay, so let's move on to set 2 linearly independent categories. And so again, we'll take a break, and then we'll come back, a bit longer break, and then people can get working on things, clean up what they have from the previous round, and then move forward to set 2. And then when we come back from the break, we go 1 round and then we share. So let's take a longer break now. Let's see, it's 10:22. Let's do 20 minutes. So we can take 10-minute break and then continue coding for 10 minutes. And then we see where we're at. You can, of course, feel free to discuss or whatever, work together if you want, or you want to continue working on your own to sort out the previous round of bugs or whatever. Please feel free to do that. Okay, so we'll come back at 10:40 and catch up with everyone again. Okay, let's continue, guys. How are you doing? Very interesting. I hope you're having fun. I think whatever it is, I hope it's fun. Okay, it can be wrong, but if it's fun, that's all you need. Okay, so let's carry on to one more round, and then let's see if we've moved on to set 2, or if you've solved your previous problem. Shall we go again, same direction, and then see where we are at? So 那边要不要接那个？那我看我怎么还过去。Again, it should be this one. No progress? It's fine. It's fine. Let's just keep going. And then if you have some problem, we can raise and then we can see. It's okay. The cable is not connected behind. 后面那个没有连。有了。Okay. Yeah, use the mic.
I built a multi-layer
Yes.
perceptron
Okay.
with 20 hidden units,
Yes.
and
Does it work better?
I think it maybe it's better.
This one is pattern 1.
Yeah,
Yeah. Okay.
pattern 1, and this is distorted one.
Okay.
So
Yeah.
Yeah.
So compared to the one you did just now was just a 1 layer.
yeah,
And it has some weird output, right? So this one looks like it's performing better, right? Yeah. But I mean, again, it's a statistical thing. You might want to try a few times and see if like it really is performing better, or is it just by chance?
okay.
Yeah.
Okay, I think that's fine.
Okay, good. And so the suggestion also is that since you have the setup there, you might want to try having the visualization so it's easier for you to, every time you try something, it's easier to see.
Oh, okay. I have
Yeah, you have a
one
question?
more question. And for this,
Yes.
because it's overlapping, and
Correct.
this two is in the same position, is it still
Oh, sorry.
not overlapping?
Oh, did I do something wrong? Oh, no, it's non-overlap. Oh, this is weird. Is that okay? Is that better? Okay, it's non-overlapping because it's non-overlapping with the other category. Within the category, it can overlap. It's fine. Correct. So although that position in category D has 2 ones in the same position, that position has no ones in the other categories. So that's what the non-overlapping means. Okay? Yeah. All right.
Thank you.
All right, let's get on to the next person. This is good. You guys are actually doing pretty well considering, that this is like the first time doing neural network, this kind of thing. So, and you are getting it, so, feel good about it.
Well, I don't have too much progress, but
Sure.
Okay, at least that's what I have. So I add the distorting input testing.
Yeah, okay.
So where's the?
I see a distorted
So the
input.
distorting input is actually the same.
In this case,
Yeah.
you want to try again to make it not the same?
Okay,
Okay,
now
there
it's
we go.
different.
Okay. And is it
So-
okay? Is it?
Yeah, I
Look,
think it's
0,
still
1, 0, 0. Okay,
Yeah, it's still 1 0 1
Okay.
0 0.
great,
Yeah,
great. So it's behaving
Yeah,
as expected.
yeah.
Okay, good.
And in the second part for the different eta value,
Yes.
I also add the distorting.
Yeah. For
Distort.
the other, the hyperparameter.
Yeah.
Okay.
So for different input, the same input but different eta, the learning rate. If the learning rate is smaller, the output is not quite close to the 0,
Okay.
but it's better.
As expected. Okay.
Yeah.
Good.
And the distort is also the same.
Okay. Yeah. Okay. So it's all making sense, right? So
Yeah.
far. So yeah, find a way to summarize those results and visualize them.
Okay, so now the distorting input is different. So
Yeah.
I think it's still 0 1 0 0.
Sure.
Yeah.
This is something you might have to try to tell. Oh, so you also got the graded.
Oh yeah, I also
Cool.
I also tried.
So can we
away.
tell now which
Yeah.
one is the one that's performing the best?
I think it's the yellow one.
So it's the 0.5.
the lightest one. Yeah.
Okay, so it seems to be like the best learning is if you learn half new things and still hold half old things. Is that correct?
Yeah.
Is that what you would say based on this one?
Yeah, if you adjust the learning rate higher, then you learn faster, right?
But will it be problematic? Did you have the setup where the learning rate is greater than the momentum?
Oh, not yet.
Oh, okay, so you want to try that?
Oh, I think it will be bouncing around, right?
Yes, that's what we expect. That it will, because it doesn't hold back, it jumps too far
Yeah.
each time. Let's see, I don't know. This is what you expect.
Okay. Then I will just
But then
add
let's
more.
see if it turns out that way. That'll be very interesting. Okay.
And also the third part, I'm still working on it. I'm not finished yet.
Mhm.
But I'm going to test the different units in hidden layers.
The architecture itself, yes.
Yeah.
Yeah. Okay.
So I'm still working on it. Yeah.
So if you are trying that already, so the way to think about it is the 10 and the 4 are fixed, right? Okay,
Yeah.
the input and the final output are fixed. You have freedom to, and then the things you want to try would be, first, how many layers,
Okay.
and then how many units in each layer, right? And the way to organize that would be, we think of it in terms of the shape of the network. So you can be a kind of in this case it's 10 to 4, so it will always be a shrinking funnel, right? 就是 from wider to a more narrow kind of projection. You can try it exact linear, like that, like a triangle shape. Or you can try it like it's more narrow and then it expands. Or it expands, then it shrinks. Okay? And so that's the basic one if you only have one hidden layer. If you have 2 or 3, you can try a smoother, contraction, or kind of a very steep and then expansion, or smoother, and then, you can vary those things. So there's a lot of room to play with in terms of that. The thing is, this training set is so limited, you will probably not see so much difference from that. Yeah, that will come in only if you have more complicated training sets. Yeah, but those are something to think about.
Okay, so different amount of layers first.
Yes.
So like 10
10, 5, 5, 4, yeah, something like that. Yeah, and the way to organize it is the idea is the size of your layer and the numbers of your layer is about contracting or expanding or maintaining, right? And think about that. Think about that in terms of the information that the network is having to project. It's projecting from a high 10-dimensional space to a smaller 4-dimensional space, right? But before that, maybe it first expands a 10 dimension to a 20 dimension, then contract to 4 dimension. So that's how the information is able to be projected and then separated and processed. That's the, when it comes to the hidden layer, that's how we think about it. Does that make sense? Okay. I should try until your computer cannot. No, whatever is reasonable. At this stage, you know, you're experimenting, just do some, and then the problem is relatively simple. So my suggestion is like 1 or 2 layers. You don't need to do too much more complicated. And then just where the hidden layer is at first smaller or larger.
Okay.
You know, yeah, something like that.
Okay.
Okay?
Okay, sure.
Right. You want to try? Still no? It's fine. Okay, let's go on to the next person. Yeah. Huh? Oh no, they have microphone here, yeah. Okay, just swap over to the other side. And I think we need to set it so that, hang on. It's okay. Now HDMI and yeah.
And I set the 3 category. This is the first one is not overlapping, and
Yeah,
the second
okay.
one is the linear, and the third one is the non-linear.
Oh, okay,
Yeah,
you went on to that one. All right.
And choose the one layer first.
Sure.
And I just compare their
Very nice.
error time score on this. So the pattern 3 is not decrease close the one, and the pattern 2, the linear, is the better than the pattern 1.
Can you tell me what is the difference between the 3?
The one is the non-linear, non-overlap.
Non-overlapping.
Yeah.
Okay, but with a single layer. Okay.
Yeah, single layer. And
And
the second
2
one is the linear one.
Linear independent.
Yeah.
Okay, and then
The 3 is the non-linear.
okay.
Yeah.
Non-linear. So yeah, okay. So that the output is just 2. Okay.
Yeah, yes, one layer.
Okay.
And see, so
Very cool.
the pattern 2 is like the better.
So do you want to try out with the 2 things to think about?
Yeah.
So first, it is somewhat expected, but also a bit unexpected, right? Because
Yeah.
so you would expect like this one would be similar. This first 2 should be okay,
Yeah.
because the first one is non-overlapping, so it's also linearly independent,
Yeah.
right? So in fact, 1 and 2 should be almost the same.
Yeah.
But it seems like there's still some difference.
Yeah.
And so then the question is this by chance? Is it just this one time you try it, or every time you try it, it's like that?
Okay.
Okay, so you want to have it in your code to loop maybe a
Okay.
few times to see how robust these patterns are.
Okay.
With respect to the last one where it's non-linear, right? It's
Yeah.
expected that it's doing the worst.
Yeah.
So we expect that to always be the case.
Yes.
So that one, in terms of trying a few times to see if how robust this pattern is, that's one thing to try. Another one, obviously, is if you do the hidden layer now instead of just the single. You did? Did you do that?
Yeah. Yes, hidden layer.
Okay, great.
But I
Oh.
try the distort layer first. I try the
Oh, this is
distort-
the square error. Okay.
Yeah.
All right.
Try to see their means in the different 3 pattern, but the soul is like I don't know how to
This is square error.
explain this result, because look like they in the different fit up,
Yeah.
they have the different mean square error.
Oh, do you know why? Because this one, the squared error is about the output, right?
Yes.
The output minus the actual output minus the target output
Yeah.
square and sum it. Is
Yeah.
it sum?
Yes, sum.
Okay, so because you see the sum here is only for 2 items.
Yeah.
So here is for 4 items, 4 outputs.
Yeah.
So you expect that the total sum square error will be smaller for the green one by a factor of 2. And you can
Yes.
see, yeah, it's about twice, or maybe sometimes 3. Yeah. So one thing is maybe you can't just do sum of square. You have to do divide by the number of units. So here you need the number of degree of freedom. So here you need to divide by maybe n minus 1, so 1,
Yeah.
which is the actual number. And here you need to divide by 3, n
Okay.
minus 1 degree of freedom. And you will see probably that they will be about maybe
The
not
more
so
close,
different. Yeah,
yeah.
maybe. Maybe that's one thing I can think about.
Okay.
Yeah. Yeah,
I will
because
try later.
this is good. You see something like this and then you're like, hey, what's going on? And then you can see how maybe that's something to do with the error term. Another interesting thing is, what is this axis here?
The change in the fit up, because sum is pattern 1, I changed to 0 to chaining to test.
Yeah,
Yes.
number of flip.
Because like the
Oh, I see.
original
The
pattern.
percentage of distortion. Is that
Yeah.
right? So this is like 0%. This is 10%, 20%.
Yeah. Because
Okay.
the input is 10, so change the each one so they can choose the 0 or the 1 or the 2 to fit up.
So if this is 10, that means these patterns are
different.
exactly the opposite of the original pattern.
Yeah.
So this is cool. You expect, so humans learn like this, right? If I have an original pattern, I can recognize this as a cat.
Yeah.
If I have a reverse cat, that's whatever that means, okay? Which is in this case 10, right? It's
Yeah.
a negative cat. We can still recognize it's a cat.
Yeah.
It's just negative cat. So I give you a photo of a cat, and then I apply, negative color the image, but we can still recognize it's a cat.
Yeah.
But here this is saying this network cannot do that.
Yes.
It's very different from us. So obviously we are doing something different, right?
Yes.
You would expect for a human, it will be more of an inverted U shape. That actually the worst will be the halfway point. But once you get to the negative, we suddenly recognize that it's just the same thing, just negative flip. But the computer here, at least this network, cannot do that. Yeah, that's interesting. So think about that.
Okay.
Okay, anything?
Yes, have the 2 layer, they saw the total error times course.
Yeah, but
Here
it's,
can see the pattern rate also is the
yeah, it's
worst.
still being replicated, right? So this is
Yeah.
curious, and then you see whether this is robust.
Yeah.
Okay, and it might be that you are using the fixed learning rate or a different. You can try different learning rate, and you see how these lines change also.
Okay.
Yeah, very cool. All right, next.
Hello.
Yep.
So,
Okay, here we go.
where were we? Let's see.
Yeah.
So I collect. One sec.
Yeah.
To compare the model with and without hidden layers.
With and without
So
hidden
I
layer, okay.
calculate the sum of square error,
Yes.
and the square error with hidden layer is 0.06.
Yes.
However, the square error without his hidden layer is 0.5.
So big. Yeah.
So
It's
it's
expected.
significantly higher. Yeah.
Sure.
Also, I average the total error 3 times,
Yes.
but surprisingly, the without hidden layer ones
Yeah,
still seems perform
pretty okay.
faster and pretty okay. Yeah.
It's not faster, it's slower, right?
It's slower.
This is the blue line is slower.
The blue one is with
oh, with hidden. Oh, I
layers.
see. Oh, okay, okay.
Yeah.
Right.
Surprising. And also I was doing
Why do you think? You think any idea?
I am guessing about maybe it's because the training or
Yeah.
the testing is too easy.
Yeah.
We don't need a hidden layer to
this
do that.
this one is
maybe.
for which pattern set?
For pattern 1,
So the
non-overlapping.
non-overlapping. So maybe if you have a more complicated one, the difference would come out. Like for her,
Maybe.
you did the non-linear and then the other one, then you see those differences. So maybe a more complicated one when you compare it, it might be different.
Okay. So also I was writing. Let's see. With distortions.
Yes.
Trying with distortions.
Yeah.
But it seems kind of weird that I set the P to 0.5. However,
I mean, that just means
random.
completely-
Totally
yeah,
random.
just no more original
But-
information.
Surprisingly, the
It's-
model still perform okay. So that's not supposed to.
You want to
be
check
correct,
whether
yeah.
you're doing it right.
Yeah, something is off here.
Okay.
I'm checking it.
Yeah, if it's not as expected, it could be that you learn something new, or it could be your code is wrong.
Yeah,
So which means that you need to go back and validate. Yeah.
something is off here.
Yeah.
Still checking it out.
Okay. Okay.
Okay, that's it
Is that
for
it?
now.
Okay. All right. Great. All right. Very exciting. Okay. Next.
Okay, so
Okay.
I think I got it all set up this time. So I have
This
the
is
new.
non-overlap. Okay. Yeah,
Yeah.
that looks right.
What is this? Oh wait,
Whoa.
sorry, that's something else. Yeah, okay. Single layer perception,
Yes.
visualization,
Yes.
and then two layer
Two
or
layers.
multi-layer perception training, and then yeah, here's the evaluation. So have the squared error and
Let me
everything,
see. Okay.
and let's see.
So
the-
this is one layer,
Mm.
and then this is the desired output. Does it do it? Yes.
Mhm.
Okay. And
Yeah.
then yeah.
The
Okay.
two-layer
Two-layer,
squared error
okay.
if it's
Got it.
lower. Yeah.
Okay.
And then distortion added like 50% probability.
Which is completely messing it up, right?
Yeah. Oh yeah.
So you would expect it shouldn't do very well.
Yeah. Well,
Is that right? Yeah. It looks like it's yeah. Okay.
yeah, a bit harder. Yeah,
Well, you
yeah.
can see it's doing something weird, right? Very
Yeah.
very weird. Yeah.
Yeah, squared,
Okay, there we
squared
go.
error is much bigger.
Yeah.
And then, yeah, comparison of the two.
Okay.
Hmm.
The internal learning is still yeah converges, but
Hmm.
two layer. Hey, so you are getting similar as what William gets, right? Some slight benefit or advantage of the one layer compared to the two layer. Very, very subtle, right? So this is interesting. But this because you are testing on the linearly non-overlapping case or whatever. You see how this might change if you do the linearly separable or the non-independent case. Yeah, that would be interesting. Okay. Anything else?
No, that's it.
Okay, very good, cool. Okay, guys, let's go on to the next assignment part, and then let's see how far we can go, because I think we're doing very well. Okay, so if you have done set 1 and set 2, okay, then for some of you, you have done up to set 3, where they are now non-linearly separable. You will note that, and some of you have already picked it up. When it comes to this one, for set 3, it is still a 10-bit input, right? But the output is now about only 2 categories. So in other words, now the architecture should change. It is not going to be a 10 hidden 4 or 10 4. It's going to be a 10 hidden 2 or 10 2 network, right? Okay, so this is how you would frame the data table. It's a bit different. And beyond that, there's also another change, which is that now the categories, the activation state of the units are overlapping, and they are non-linearly separable. You can see that because, why is that non-linearly separable? Is you can sort of get it even if you just look at it intuitively, visually. This is 111000011. It's like, effectively, it's like cat and non-cat are all cats. And then like dog and non-dogs are all dogs. So can the network separate cats from dogs? Think about it. Even as a human, you will probably find it like, wow, this is impossible, almost impossible. Cats and non-cats are cats. Dogs and non-dogs are dogs. How do I separate cats and dogs, right? So this is the problem, right? And so you can see that your model might not perform as well, or at least that's the expectation. And you can go try it out, all right? And then come to your conclusion. But I want to move on to this next part first. So try that out if you haven't on your own time. But we can skip ahead a little bit in this lab and take a look at this one. So now this one is asking you to specifically do 838, okay? And the input is these 8, and the output is these 8, okay? So the data table is like that. And do it this way. So like make it such that it's 1, 0, 0, 0, 0, 0, then 0, 1, 0, 0, 0, 0, 0. Then etc. means like, then the next pattern is 0, 0, 1, and 0, 0, 0, 1, right? Okay, so you get a nice diagonal for the inputs all the way until this one. You reach the 7th position for the input. So, and then the output is the same. So essentially, this is kind of like an autoencoder, right? This is saying map the input to itself, which is autoencoding. So it's an 838 autoencoder, okay? You can explore the parameter space. You can do learning rate 0.1, 0.9, 0.5, 0.5, up to you, the eta and the mu, okay? But try it around, okay? Then this is saying that you should train it on all the way until the 7th position active, but don't train it on the last position, you know, for now, for the moment. Now, the question would be, does the network learn the correct input-output mappings, and again, how long does it take? So you have that iteration plot. You can check when it settles, all right? So try that out at least. Does it do the auto-encoding? Okay, so let's just try that first part first. So it should be easy for you to do 838 with the setups that you already have. Then now do the data table as the first 7 input-output patterns. Okay, so I'm going to let you guys try it for about, I would say, 10 minutes. And then let's see. This is exciting. Let's see what you get. Okay. If you are already very fast and you do it, then you want to, the next question is test it on the final untrained output. Okay? But for now, let's focus on the first 7 first. Let's do 10 minutes and then we'll check one round. How do people do on this? Okay? Oh yeah, so in this case, it's not like, just to reiterate, and it should be obvious, we're asking you to do 838 on a fresh network. So none of this should be pre-trained or anything. Okay? So a fresh network, 838. and if you need to take breaks, feel free to, you know, take breaks if you need. We'll come back at about 11:25, okay? Now it's 11:15. Okay. All right. Shall we carry on with that part, the autoencoder, and see how people are at, where people are at. Okay. Yep. Okay.
Yeah.
This is the input.
Yeah. 7
Yes.
patterns,
And the output is the same, basically.
Yeah.
Right. Yeah. Okay.
so this is my architecture.
Very good. 8, 8.
And distort at 0.2.
Uh-huh.
This is a first.
Let's see. Does it do it?
Not,
Oh,
not so good.
not so good, but not too bad. I mean, it is sort of doing it something. Oh, but if you distorted it, so this is the distorted
Yeah.
pattern, right? What is it doing? Oh, so this is interesting. So with the original pattern, it is sort of doing it, but maybe there's some problems. But you know, still, if you were to binarize this by 0.5, it's okay actually, right? But here it's very interesting because your distorted pattern is 1 and then 1, 1 here. It is sort of 1 and then doing 1, 1 also, right? This is interesting, okay? You can pursue this and see how it goes. But at least, so for distorted patterns, it's doing something not expected. It was not trained on this, but it sort of gave you back the same, same thing, right? But at least within the original pattern, it seemed to do that. So that would be interesting. So you might want to try maybe a few more times again and see if this is robust. There's some phenomena where it seemed to learn, just repeat what you give me. That kind of thing. Yeah. Okay. And then
I try.
the last pattern.
Yeah. But I still figured it out.
Oh, okay. There's there's a bug, or is it a bug or something?
No.
Or you just haven't tried it?
Yeah.
Oh, okay, okay. That's fine. All right. So pretty good. So what do you think? Does it do autoencode?
It's error.
Ever? Well, right now you're doing 8 by 8. You should try 838. See if you can try 838 instead of 88.
838?
Yeah. The assignment there says 838.
Why? But I didn't train.
Yeah, it's easy. You just do that and it will. No, you have to train it by 838. You have to do the training by 838 and then you test it by 838. Oh yeah, so there's some bugs here you might have to sort out. Maybe it's to do with the input and output. Oh, no, I know. I see. Okay, can you go back up to your initial one? I get it.
This?
Okay, no, yeah, okay. So here you have 7 inputs, 7 outputs, right?
Yeah.
Okay, so if you go down to the training for this one, no, not too far. Just that,
This.
no, for the first set. For the first 7. Yeah, okay, so here you train it on the 7 inputs, 7 outputs.
Yeah.
And do 838 here. Yeah, try that. And then visualize the 838. Okay, so it should be 838, right? Yeah, like this. Okay, so this is what we want to test.
Oh.
And then you
Test again?
and you test it. Yeah, you can do the testing. Okay. All right, and then you see you can. Yeah. You have to change. Okay, so you want to do the test net here, and you want to do the test net here, and you see how. Whoa. And you want to check how it performs. Then for the pattern 8, what you want to do, so if you go down a little bit,
Go down, little D.
yeah, you don't want to actually train it. You only want to test it for
Oh.
pattern 8. So in other words, you train on the first 7 patterns, and you can test the first 7 patterns. But for this pattern 8, you don't want to train it. You just only want to test it. So yeah, you want to see like if it generalizes. So like if I teach you the first 7 ones, right? I teach you the answer to the first 7 problems, but I don't teach you the answer to the 8th problem. Can you tell me the correct answer if I give you the 8th problem still? So I don't want you don't want to train the 8. You want to only test number 8.
Okay.
Got it? Okay, try that. Okay, next person.
Okay.
Okay.
I still don't have quite much progress, but
It's okay.
So why? Okay, so I tried the different amount of layers.
Yes.
Well, not units, but I think haven't changed it. But
This is the 10, 5, 4, 10, 5. Okay, got it. Yeah.
okay, so and there's a result. I try to visualize it by the arrow.
Oh, so it gets worse.
Yeah, for some reason I don't know why. It's weird.
Why do you think? You don't know. Okay.
I don't know.
We haven't covered it yet, but overfitting is one possibility. That the network might be overdoing what it needs to do. So are you doing this across the distorted patterns? This one is from the distortion. Are you testing it on the distorted pattern or original pattern?
Oh, let me check.
Yeah.
I kind of forgot. No, the original one.
Oh, the original one.
Yeah.
And it's still doing that.
Yeah.
Huh. Interesting. Let me think.
It's
And
my
your eta and mu are set to be the same?
0.
0,
point-
3, okay, and
yeah.
7. Do you have the energy plot, the time course? I'm wondering if they didn't settle at all and then it stopped at 1,000. And therefore you get a bit more error. Is that a possibility, you think?
I don't know.
Okay, maybe that's something to check. When go back to the time course plot for the different networks and see if they all show the log
Like
reduction
they run
factor.
the whole 1,000 epoch.
Yeah, and whether they run the whole 1,000 and they settle. I mean, I would be curious about that. If the
Okay.
errors are so big, it suggests that they are not settling by 1,000. They still haven't reached the
Oh,
0.001.
so they may need more epochs, not just
Exactly,
1,000.
because now you have more weights to train.
Okay. I
And so
see.
they may need more epochs to really settle. It could be. I don't know. Just suggestion to look at.
Well, if I just change it to like another 0.
I don't know. You could try that. Yeah. Those are one ways to try. You could increase the number of epochs. You could check the epochs to find out how many do you need. Yeah. With more parameters, you need more training, obviously. So, but then we don't know how the interactions happen.
Okay.
Yeah.
Okay. I
Does it
think-
take very long?
Yeah, I think it takes some time.
Oh yeah, because now it's 10,000.
Yeah.
Okay, all right. Well, we'll come back to you.
Oh, but I got the
I-
question too.
Oh, okay, all right. Let's carry on.
So, it's
Oh, there
finished.
you go.
Oh, it can still.
It's
much the same.
still. You have to see the the
Okay.
performance to decide what's a good parameter set to try.
Okay, sure.
Yeah, okay.
I will take a look.
Okay, but this is interesting. This is interesting, and you would not have known unless you try it and then you see it. And it could be because you're doing 555. Maybe you need the compression or expansion. Yeah, yeah,
More
Yeah, yeah.
units.
yeah.
Okay.
Yeah.
So the question 2 is try the
838 autoencoder.
and with the oh.
Hmm?
It just anyway. So I think the input and the output are the same, but
Yes.
where's my input and output?
Input Q2.
Yes, but anyway, I think I accidentally did it.
Oh,
but,
fine,
But
yeah.
anyway, I still have the previous result.
Yeah, and it's.
So
Is it correct?
if I test the test the network with the trend input,
Yes.
it will be the same.
Okay.
But if I don't use the trend input, then the
It's not.
expecting value are going to
Okay,
be.
so it seems like it didn't learn to generalize to the last output.
Yeah, it does.
The last state. Okay, let's see if it's robust and if you have a few other ways to that. What would you expect? Do you think that it should learn or shouldn't learn?
I think it shouldn't learn because
Why?
it doesn't remember the unchained pattern.
Yeah.
So
So just like the just now, sort of, she already did it. Like when you distort it to the opposite, it seemed like it doesn't generalize some higher level thing.
yeah,
At least just like that, right?
yeah,
So it's like it only still remembers what it was trained on, but it's not able to generalize so well. At least not in this kind of. It can generalize within the noisy distortion, but it cannot generalize across category. Right? Is that fair to say? Yeah.
yeah.
I think that's one thing we can appreciate. So yeah, explore that concept. I think this is very interesting, and you can see how you can play around with it to test those ideas out. Because also remember, LLM, what we want is generalized, right? You want to say something, but I want you to also be able to get what I didn't say, right? It seems at least this backprop is not as good as current LLMs, because current LLMs can do that, but this one cannot, right? So what do you think would be what are they doing differently that we don't do here? Apart from that, okay, they have massive data and massive compute. Is it just massive data, more complex thing, and maybe that's what it is? Or is there something more fundamental? I don't know, we can think about that.
Okay.
Yeah.
Yeah.
Okay, anything else? Okay, all right, good. Then we go next person, over here. You want to go first? Sure.
Yeah, because I also did the same thing as you, and I checked out other like
Okay,
numbers
let's
of
see,
hidden
very
layers.
interesting. Let's see
Yeah,
what happens.
and I have a time course for it, so I don't think it's the epoch problem.
Okay,
Because, yeah, because
cool.
my time
Let's
course
see,
is,
what do you find?
yeah. Hmm.
It messed up, but maybe it needs more units, not more epochs?
Maybe.
I don't know. Let's see.
Okay.
Did it work? Oh, this is the time course you have?
Yeah, yeah. So like,
Ah,
Stuff like that.
interesting. Okay, so it looks like it still was able to settle,
but it didn't look very.
but was the performance okay?
This is the output. Not really.
This one you're doing this one is the autoencoder, is it?
Yeah, for the this one.
Which one? Okay, all right.
Yeah.
And you're doing this 858, and you have this is the last one. So it's also, again, it's not able to generalize to things it was not trained before. At least in this case.
Yeah, yeah, yeah.
Okay,
And
interesting.
same with I added 10 hidden
Yeah?
layers too, so that's
Okay.
what it looks like. And make sure that's okay. Yeah.
And
also
still not
didn't
doing
get
it?
the
All right. Yeah.
not the right result. And I
Okay.
think worse, right? Yeah. About the same.
Okay.
But anyway, yeah. So this is the original 838.
Yeah, can it do at least the original?
Yeah. Also no.
Can it test? Can it recognize itself? What if you do 1000 instead of 001? Yeah. Not so good.
Yeah, not so good.
Okay, this is interesting. What would you expect though? It should at least be able to recognize itself, don't you think?
That's true. Yeah.
Yeah.
You
I don't
train
know.
more. I don't
You wanna go check out if on this front it's not performing the basic. Is it because maybe is that we are testing the wrong thing? I don't know, but go check it out.
Okay.
Because the expectation should be it should be able to learn itself because it can map anything to anything. Okay, but if you didn't train it on things, then yeah, maybe that one we expect it might not be able to perform, but it should at least be able to map things that it's been trained on, right? That would be the expectation.
Okay.
Or maybe it can't. Maybe you try and really can't. I don't know. So you go check if that is in the way you've set it up, whether that is correct. Okay. I mean, the rest of you can try too. Did it at least learn itself? It seemed like it did previously. Okay? All right. But your time course also looks a bit interesting because everyone is doing this like L shape. You are having kind of like a interesting kink here, like, in the curve. You want to check out also whether are you implementing it in the same way as others, or whether there's something different in the way that this error is going. Yeah, this is interesting.
Okay.
Anything else?
Yeah, this is the one trained on these two mappings.
And
Yeah, time course looks.
and that you get that
natural.
one. So and how does it look? Does it perform?
I tried with this.
It's still not performing. Yeah, very weirdly, right? Isn't it?
Kind of weirdly, yeah.
And this is not distorted, right? This
No,
is
no.
directly just training. Yeah. So think about that. Like, it is not. Look at that, right? It's not very good at all. Yeah. So go back to the original things to see, like, is there something up with the network that is being implemented? Maybe it's the shape thing or whatever it is. And then see if it is performing as expected for the foolproof cases. And then when you try these, like, it's breaking, or and why is it breaking and all that. Okay, pretty cool. All right, anything else? Okay, next.
Part 2. So as Benjamin's results,
Yes.
my 838 model is not performing well either.
So that's coming classic.
So
Alright.
the input data is 0 to 7,
Yes.
but not 8.
Okay.
So if I collect all errors,
Yeah.
3 AirPods,
Yeah.
it
Oh,
also
you
shows
get the
these
same thing
kind
as
of
that. Yeah,
weird,
yeah. So
weird
you guys
shape.
there's some correspondence here.
Yeah.
Okay, good.
And this is without distortion, but it's still not performing well. And our testing target is the 5th
Target
one.
is that one, and the output is.
But the output is the error is the absolute of error sum is about
this,
2.
Is this the actual output?
This is the
Okay, so
predictions
Yeah, because you can see.
of
Look.
AO. Yeah.
Yeah, look at. You can see that this should be 1 1.
It's more like
this
1 1.
This should be 0 here, right? It is close to 1, right?
Yeah.
Yeah, so it's also not. So it's
Some
not so
error.
good at
0.5.
auto encoding, or at least in this setup, it seems.
True.
Is that what your conclusion would be? both of you guys?
I checked my code several times. I think it should be correct. It should be correct.
Okay.
So, I don't know.
No, you have to have
Blame the
some level
model, I
of
think.
confidence in your coding, and then you make a statement that
I can blame.
I've done this, yeah,
the
and
model, okay.
I have to conclude that it doesn't do it, or
Do
it
well
does do it,
in
yeah, okay?
These kind of text.
Yeah,
And
yeah,
also I
that's fair
do
enough.
distort,
Yes,
but even if with 0.5 distortion, so it's basically randoms.
yeah,
Of course, it still perform relatively bad.
okay. Okay.
So that's it for now.
So there seems to be that originally it was performing okay, but then now that we're moving into many more complex type of data,
Mhm.
it seems to start to show some breaking, right?
I don't know, but this kind of input data seems easier, doesn't it? I don't know.
I don't know. This
It
depends
seems easier
depends on
and
easy-
without
we-
overlapping. but-
We always think it's easy because we are so-called intelligent, and right, and then maybe we take things for granted. Maybe it's not so easy. It's easy to
Uh-huh.
us. Doesn't really mean it's easy per se.
Okay.
Yeah. Okay, cool. All right. So there's still work to do, but yeah, you guys are having the good fundamentals. So, okay, last one. Yeah, I think and then we're doing good on time. So. What do you get? Same thing?
Almost.
Oh yeah, so that's nice.
Yeah.
Yeah, so you get that.
A38.
So we have 3 validations now. So
Yeah. Need more time.
So it's good to work together, right? Because you say other people do it and get the same thing, so you feel safe. Okay.
Yes.
And,
And here I
yeah.
use test the chaining pattern, and
Yes.
the mean square is 0.18.
1.8. Yeah.
Yes, and also test the on-chain pattern. The mean square is higher, and I also compare together. So this
very
auto
good.
auto model is hard
Yes.
to test the on-chain pattern, because I
Yeah.
think it doesn't have any luggage inside.
Right.
Yeah.
Right.
And the next part question to use different on-chain pattern, and I just decided to find on-chain pattern to test.
Your own. Yeah.
Yes, and also to compare the different pattern,
Yes.
and also they have the very high like the mean square.
Yeah, you can see. Yeah,
Yeah.
it's
It's
really very
totally
different. Right?
different.
Yeah, yeah. I mean, that
To
one's not
compare.
bad. The last one. This one's okay.
It's
But it's still
more
wrong.
similar. Yeah.
Okay.
Yeah,
Okay.
and to compare the mean
Yeah,
square.
yeah.
Yeah.
Yeah,
That's
you
a
can see
high.
that is
It's more
best,
close.
but yeah,
Yes.
still bad.
Yeah.
Nice.
Yes.
Oh,
Just-
okay.
Yes.
Oh, all
chain
right.
here.
Excellent. Yeah.
Yeah.
This is very cool. I think, yeah, we are seeing very interesting things happening, right? And we're seeing like, hey, different people are doing different things, and we can see how this network can behave very differently across different situations. Yeah. Okay, so I think in terms of the assignment, I think we are doing very well. Everyone's doing pretty cool. It seems I get that like I think everyone gets it, okay? And in fact, by doing all the way to the end, you've pretty much finished close to the end of assignment 2 already. It's just that obviously it's very rough, but you can formalize it and make it and just really complete assignment 2 more comprehensively on your own time. So I'm not too worried about that. Okay. So any questions about what the exercises that we've done in lab today? Any questions? Anything that you don't have confidence about, like where to go from here in terms of the assignment? I get a feeling that everybody should be all right, and you just need time to figure it out, right? Yeah? Okay, so this is great. It's fun, and I think we are seeing very interesting things about. We have an ideal from the Hinton's original proposal that backpropagation allows you to pretty much learn anything, but it seems like maybe that's not the case, right? Maybe there's something so you see how this is, why this is requires simulation. You have theory worlds where you have all these nice, you do this, derive the equations, and then you say in theory, like if you do a gradient descent, you can learn anything. You should be able to learn anything, right? But there are limits when we actually run it. So you will never know until you implement it. And this is why you need to run neural network simulations rather than just based on mathematics, yeah? So in this case, there's meaning because the point where this network seems to be breaking are things to us which seems very intuitive. If you learn this category, why can't you learn this other category? It should be very intuitive to us. But to a network like this, it seems that that is not enough, okay? Suggesting that if we assume that our brains are neural networks, suggesting that it must be that this network has some basis, but it's missing some other architecture or some other things. What are those things? And so, that's for us to explore. Clearly now we have the benefit of, we see that LLMs, which are sort of backpropagation based, can learn something, but very more complex. So this is very curious. What is so special? Is it just because they are much bigger, or is there something fundamental that's different about the way they operate due to the size than when we have small sizes and things like that? Okay? So yeah, obviously a lot more to cover, but these are the basics when it comes to backprop. And we are experiencing it firsthand in terms of like, although it's a nice beginning point, but it seems to also still have quite a lot of limits. The challenge here to you guys is this. Can you, within these setups that we have, overcome those limits? Like maybe we increase the depth, right? More layers. Maybe we have a very special number of shape of the network. Maybe you need to expand, compress, or whatever. Or maybe you need some sort of tweaking of the learning, the eta and the mu and things like that. And then you find that under these circumstances, the network can learn best. Under these other circumstances, the network can learn best for other kinds of problems. That's also interesting, right? Many things to play with. Yeah. Okay. Any final questions for today based on these lab exercises? All right, so then the expectation is, we're going to close the chapter on backprop. And in terms of assignments, I remind you guys, Hopfield is due tonight, midnight, okay? So far, I think people should be okay. And then you can turn to the backprop assignment, which will be due in 3 weeks' time at the end of the von der Mausberg one, where I will open that one, okay? So I think you guys look like you get it, that you have this cycle going and you know what to do. So I think that should be all right for the assignments, okay? But of course, we don't want to assume anything. If you do have problems, as always, feel free to email or write or directly communicate in class whenever we meet. So next week, we will be moving on to von der Mausberg. And I want to highlight von der Mausberg's, I want to bring it up first, and then we'll call it a day. Von der Mausberg's paper is very interesting because I think this is the key thing. Where is it? Here. Okay, figure 5. Okay. Von der Mausberg's network is very different from Hopfield and backprop. In a sense of the goal here is really a different class of problems. It is not about the learning rule, and it is not about the architecture or the activation function. It is about something more abstract than that. Specifically, it's about the fact that you can see this is a vertical line, and these are rotating lines, right? This is not about learning activation function. It is not about the architectures. It is about the architecture per se, but it is not about the learning function. It is not about the activation function, okay? But somehow, because of the way we will organize or set up the network will have what we call orientation selectivity, which is something you know if you guys know the neurobio. V1 neurons have orientation selectivity, right? We will watch a video next week and you will get what we mean. Some of you might have seen it before. And the idea here is this is what we call unsupervised learning. It's learning something that we didn't really explicitly train it to learn. So there's no theory, there's no formula about the way you will see how this network plays out. Okay? So this is a very different class. But as different as it is, it relies actually, you will see, on Hopfield-Hebbian principles and some sort of error in a way that kind of what we were discussing. Where is this error or learning coming from? It's actually coming from itself. It's not coming necessarily from the external world. So it's a bit very kind of a interaction of all those principles that we've been talking about in a very interesting way, and it comes out as being unsupervised learning, okay? All right, so next week we will start talking about this, and as you are working on your assignments in your free time, read the paper. Von der Marsberg paper is, I would say, not as difficult to read compared to the other two. Okay, but in terms of the implementation, it will be a bit more tricky because if you saw figure 5 just now, the input is not just simple so-called n-bit words, but some sort of hexagonal shape. You will see in my implementation in the code that in the code there will be something about how to do these hexagonal grid activity states, okay? So if you want ahead of time, you can familiarize with that. But at least next week, we will talk about the theory and the concept, at least, behind the von der Marsberg network. And then in the coding, you will see it's a bit different in terms of the inputs, how to set it up. Okay, so be prepared for that. And I hope you all are having fun finishing up the assignments, okay? And from next week, we'll see you and we'll talk about this very cool, very exciting thing. All right. Okay, any final things? Okay, if not, that's it for today, and we'll see you next week. Okay? Thank you.